This conference will now be recorded.
Hello everyone, we will start with the session. My name is Srinivas. So today we'll be starting off with the RISC-V ISA instruction set architecture training. And as it has been informed earlier, today will be a demo session to give you an overview of what to expect from this course. Just give me a minute. Looks like I have opened. Please give me a minute. I'm opening the right presentation, then we'll be starting off. So in the meantime, can you please share your perspective of what is your prior expertise and what is that you are looking from in RISC-V training? So I hope everyone see the screen shared. Okay. So now we'll start off with RISC-V instruction set architecture training. And as said before, this will be a demo session to give you the overview of the training program. So let's start off with the training agenda. We will start off with understanding the significance of processors in SOCs, and then we'll understand why we are going to RISC-V. Then we'll talk about RISC-V instruction set architecture. Then we'll start off with the basics of RISC-V process. Then we'll talk about RISC-V architecture. What are the subcomponents? What are the different units in RISC-V architecture, and how the pipelining concept works. Then we'll also talk about in depth into the instruction set architecture. Then we'll talk about different instructions, different types of instructions in RISC-V. Then we'll be doing some sample examples related to the RISC-V, and we'll be compiling them and running them, and just to analyze how the conversion, any given code conversion happens into the RISC-V assembly language. Now, before we get on to the further topics, let's understand how should we look at, as a verification engineer, as a design engineer, what should be the perspective? What are the different ways of looking at RISC-V training? RISC-V learning activity. See, majorly we can classify into two levels. One is from a RISC-V ISA users perspective. Second is the RISC-V implementation perspective. So if we talk about RISC-V ISA users perspective, it doesn't require much in-depth knowledge of how each instruction has been implemented. You don't need to probably go deep into how the pipelining has been implemented, how the various components have been implemented. We probably don't have to go to that level. We have to mostly understand from the top level various types of instructions supported. And how to understand an instruction, and how these instructions work with memory and registers. Okay, how many registers are there? And how user can develop the assembly program, the assembly code targeting using these registers. So at this level of understanding would be sufficient. If you are looking from a understanding RISC-V ISA users perspective, this would be sufficient. Then you need to understand different extensions. See, RISC-V has one base extension, base integer thing, which is called as RV64I. These are base integer instructions. Other than that, there are a lot of extensions out there to support the multiply division operations, to support floating point operations. So the RISC-V provides with various extensions. So you should get a bigger picture of these things, and you should get in various extensions how many types of commands are there. When I say command, I'm referring to add, subtract, those kind of command. Let's say load or store, different kinds of commands I'm talking about. Now, when we talk from a RISC-V implementation perspective, it would be more of developing the Verilog code to support these features, support the RISC-V ISA. That means, for example, we are doing an add operation. How the add should be done? It has to be finally implemented by the RISC-V Verilog code, right? Finally, which gets converted to the RISC-V processor. So you need to look from that perspective. What are the various subcomponents of RISC-V, and how the pipelining gets implemented. All those aspects you need to look at. So our training will majorly focus on this aspect, and we will also finally touch upon this thing. But major focus will be from this perspective, because the most of the people who work into RISC-V would not be actually developing the Verilog code, would not be implementing the RISC-V hardware. Most of the times you would be using the RISC-V hardware towards the SoC development. One way is what? The SoC is developed using RISC-V processor. In those perspectives, we don't have to. Aranish, you have any questions? Okay. So when you are looking from a SoC developed using RISC-V processor, you don't have to get deep into how the Verilog coding is done for RISC-V, what are the subcomponents and all those, you should be mostly focused on RISC-V ISA. That is why I have named the training itself, we have named the training as RISC-V ISA training. So the training would focus on all these aspects. What are the various types of instructions? What are the categories? How to understand given instruction, and what is the opcode mapping, and how these instructions work with memories and registers, and how many registers are there, what is the significance of each register, and how user can develop assembly code using registers by accessing through by means of this register access. Then various extensions in RISC-V instructions, all those things we'll be talking about. Then we will be learning both the perspectives. Given a given a C program, how it gets converted to RISC-V assembly code, and next, given a RISC-V assembly code, how to analyze it. This is important because when I said you're going to work on RISC-V based SOCs, you will be developing a C program and that gets compiled and converted to assembly code. You need to understand how that is getting converted. Both these things are required for debugging purpose. I mean, both these skills help with better debugging of the SOC test cases. So this is the perspective with which we are going to start off with RISC-V training. Now, let us start off with some fundamentals of electronic systems. Before we get deep into RISC-V, I don't want to start off with any assumption that you understand instruction, you understand registers, you understand assembly code. I will not be making any assumptions. So we'll be starting off from the fundamentals of understanding what is an electronic system and where does hardware come into the picture, and in the hardware, where does RISC-V come into the picture. Then we will move on to the RISC-V instruction set architecture. Now, let us start off with understanding the electronic systems. If I take any electronic system, let's understand various layers that make up the electronic system. Every electronic system is implemented in 4 hierarchies. It starts with the very top layer. It has got applications. Then below applications, we have operating systems. Below operating system, we have embedded system, what we can also call as firmware, middleware. Below embedded system, we have hardware. So collectively, these 4 layers together is what makes the electronic system. You can't really work with an electronic system without any of them. Let's say you don't have a hardware, then there is no use of these things. Again, if you don't have any applications, there is no use of operating system. Let's say you're talking about operating system and you don't have anything to run, any application to run on that, there is no use of such thing. So every layer in this 4 hierarchies has its own importance. I don't want to tell that hardware is very important or application is very important. Everything has its own importance. Now, let us start off with understanding the application layer. When we say application layer, example of application layer is what? Microsoft Office, Notepad, VLC player, the QuestaSim tool. Everything, see, whatever you see, most of them, even Chrome is an application, GVim is an application, this PowerPoint is an application. So everything you see is an application. So the application layer interfaces with the operating system through some series of API calls. What is API? Application Programming Interface calls. Now, when we talk about operating system, you know what is an operating system, like Windows operating system, Linux operating system. Okay, operating system interfaces with embedded system layer through API calls. There is a series of API calls that happen between application layer and operating system and embedded system. Again, hardware. So this calls is what we are calling as API calls. API here, it will be a different type of interfacing, different type of interaction. We'll talk about that. There are times where the application layer can directly interface with the embedded system layer. All those things also we will discuss as we go forward. Now, when we talk about embedded system interfaces with the hardware through register writes and reads. So there will be a series of instructions which essentially will be some kind of register writes and reads, memory writes and reads through that embedded system interfaces with the hardware layer. The examples of embedded system is like USB drivers. Now comes the at very bottom layer. Bottom we have hardware layer, which implements the required behavior as per the instructions provided by the upper layers. Whatever instructions it gets from the embedded systems, it implements them. Now, embedded system in turn gets the instructions from the operating system. Operating system in turn gets the instructions from the application layer. Okay. To understand this, let us take one example. We'll take an example of one application in SOC and understand what is the significance of each layer in this application. So, as I said before, all layers are essential for proper operation of the system. Each layer has its own importance. During our course, our focus will be hardware layer. Even though I said every layer is important, but since we are going to talk about RISC-V processor core, we'll be more talking about hardware and the one layer above that. Okay, that essentially is what I'm calling as RISC-V ISA. The term ISA refers to everything collectively together. When we put together all these things, is what is collectively called as the instruction set architecture. Embedded system interfaces with hardware layer through the processor. Now I'm telling that embedded system interfaces to the hardware. Interfaces with the hardware. So the gateway, how does embedded system interface with the hardware? That point where it interfaces is the processor is the gateway through which embedded systems interfaces with the hardware. So it is the processor through which it does everything. So hence processor is very important. I mean, if the processor works efficiently, processes the instructions quickly, my hardware and the rest of the applications will run better. Otherwise, if it is not quick, the overall system performance will be impacted. That every one of us are aware of that. I mean, all of us are aware of what is the importance of a processor performance in the with respect to the system performance. Okay, now to understand how application works in an SOC, let us take a very simple example. We'll take an example of restaurant billing software. You went to a restaurant, had some items, and you went to the billing counter. So how does it work? Basically, that billing software, that is the application or the software, it is developed using either C or C++ or Java language, one of those languages. In this case, since it's a simple software, they would have used probably a C programming to develop. What would be the requirement of that restaurant billing software? Let's list down. What would be the requirement of restaurant billing software? Basically, it takes the items, it takes various inputs, number of items, and cost of each item, and finally returns the total bill. Now let us understand where is the hardware involved. Now, do you think does this require hardware intervention at all? Does this require hardware at all to work? Now, can this restaurant billing software be done without hardware? Can you tell me? Because it's a simple software, right? Can this be done without involving the hardware? Can you please tell me?
Sir,
Yeah, please tell me.
yes, sir, maybe it will be done. Yes, sir, maybe it will be done for the Android applications.
No, even whatever you say, finally it has to be. See, it cannot be done, right? Finally, whatever you do, all the calculations, all the things needs to be done at the hardware level. See, whatever calculations we are doing, the number of items, cost of item, that multiplication, let's say number of items is 3, cost of item is 20, 60. Let's say another item is 5, the cost of item is 15, 75. Then total, so we say 135. Do you think a software can do directly as it is? Do you think it can be done by the operating system? It can be done by the embedded systems? No, it has to be finally done by the hardware level, because those calculations has to happen and finally you have to get the output. Please let me know if you have any doubt here. The Ranish, I hope it is clear to you. Okay.
Yes, sir. I cleared.
Now let us understand what is the role of various layers in this software functionality. I'm taking a simple example because it's easy for us to correlate the things. I mean, entering the number of items, getting the output, everything is very easy. Hence, I'm taking. Now, the same concept will apply. Instead of this, if I had taken Microsoft PowerPoint, similar thing would have also involved there. Okay. So what happened is, first the application is developed in C language. Let us say we call it as billing.c. The name of the file is what? Billing.c. In my operating system, there is a compiler specific to the hardware, I would say specific to the processor being used in my processor being used in my system. What that compiler does is it compiles the billing.c to generate an assembly language code specific to the processor. What is meant by specific to the processor is, if you see, you might have come across various types of processors: x86 based processors, ARM based processors. Now we are talking about RISC-V based processors, MIPS based processors, Spark SoC based processors, Spark based processors, PowerPC based processors. Each of them has their own assembly language syntax. Now, what is applicable for x86 doesn't apply for ARM. What is applicable for ARM doesn't apply for RISC-V, vice versa, because each of them is different language. It's like this being one language of one of our languages, native languages, this another language. So what is applicable here doesn't apply here. It's the same thing here. So what is being done is, the compiler which is there in the system at the operating system level, it is compiling the billing.c to generate an assembly language code specific to the processor. It will give a series of instructions: add x1, x2, x5. Let's say I'm just giving, okay, this x, don't take literally x1, x2, x5. I will talk about what is x1, x2, x5 as we go forward. Okay, let's say x1, x5. If I do this like that, a series of instructions will be generated. So when I did the compilation, it is going to generate an assembly code in this format. Now, then along with the compiler, my same operating system has something called as assembler. What assembler does is, it converts above assembly language code into equivalent binary code, also called as opcodes. It is called as opcode. Opcode here stands for operation code. Right? It converts whatever assembly language code into equivalent binary code. And finally, since it is a simple application, you have only one C file. There is a possibility that my application may have many such files, right? Billing.c, billing1.c, or add.c, like that, many files, such files. All those binary codes needs to be linked to each other. That will be called as linker. So compiler, assembler, and linker. Finally, what you have is, once all compiler, assembler, and linker work is done, we have one final binary file. Why we are calling binary file is, it will be in terms of zeros and ones. It will be in terms of zeros and ones. See, finally this code may convert to something like this. I'm just telling you roughly, okay? Don't take literally that what is add here, what is x1 here, what is x5 here. Don't take literally right now. Each assembly language code line gets converted to equivalent binary code, and this collectively, that is called as the one final binary file. This binary file is loaded. This binary file is loaded into one of the into a memory location. This is also done by operating system. This is called as memory allocation. I mean, it is part of operating system memory allocation to the various applications. To the various applications. See, it's not only billing software. It's not only restaurant billing software. There may be many softwares running in my system. So it is the responsibility of operating system to do the memory allocation, where you should be running, your application should be running, where some other application should be running. All that memory allocation is done by the operating system. Now, once it is done, based on this memory allocation, this final binary file, understand, the final binary file gets loaded into the memory location. Let's say memory location is 32-tick 1200000. Basically, in hexadecimal 1200000, this location, it is been loaded. This information, what is that information? 32-tick 100 is provided by the operating system to the next lower level. What is next lower level? Embedded systems. So embedded system knows where exactly that application is loaded. Okay, it further gives, it indicates, it initiates. Okay, it initiate. I mean, it will further provide these details to the hardware. Now, in this case, what happens? Let's see. When user enters some details, let's say now we want to use the application. When I press something, when like in that billing software, when I press something, let's say I took calculator, simple here. I did something here. I went to the something called the standard 54 into 65. Finally, this calculation is getting done by my hardware only. Okay, so the 54 number is somehow getting passed on to the hardware level, and this is again, this itself is an example of an application. This calculator itself is an example of an application that is being run on top of operating system, that finally is loaded into one of my memory locations, From that memory locations, it is fetching my processor will fetch the instructions. So what happens is the processor, see when I invoke the application, the processor starts executing the binary file, and it starts fetching the instructions. What do you mean by instructions is these binary codes, opcodes. It starts fetching opcodes. The one of the opcode is something like this, next opcode, next opcode. During that process, it gets the inputs. Like I told, right? You're entering 54, you're entering 65. It gets those input, and it has got that logic based on what is the specific query raised by the user while using the application. My processor executes that corresponding operation, and finally returns the output.
Sir, I have one doubt. Hello.
Please tell. Yeah.
So the binary file is given by the operating system and hardware is doing the calculation. So what is the role of embedded layer in between?
Embedded layer, see, it is kind of interfacing the operating system with the hardware layer. I mean, see, probably for this kind of simple applications like calculator, embedded system may not be very significant. If you talk about USB, if I take an example of USB driver, you are connecting USB pen drive to the laptop. So whatever commands, the frames coming from pen drive, the operating system won't be able to understand it directly as it is. So it requires some kind of drivers. It requires some drivers, what we call as in this case USB drivers, which will be able to help that interfacing between the soft operating system level and the hardware. That is where embedded system can be involved. So in summary, I would say the embedded systems is responsible for converting the higher level application calls into lower level instructions. These instructions are finally being executed by the processor. In this case, we are talking about RISC-V processor. Okay, even when we took an example of calculator, essentially that those instructions, how they are getting converted to individual level instructions, is we can call that as the embedded system layer only. There is a very thin line difference between operating system and embedded system here, because even though I said that finally it is the operating system which is loading, the embedded system is where those instructions are being given to the processor. But I think the better example will be to understand through the USB driver, because the hardware cannot directly interface with the operating system. It requires some intermediary which will be able to understand finer details, whether the device is connected or not, what type of device is connected, whether is it we are working in full speed or high speed mode. All the decision making will be done at the embedded system layer level, and we don't want to go to the operating system to make such decisions. So that is where embedded systems acts as an intermediary between hardware and the upper layers. Does it answer your question?
Yes, sir. So embedded system cannot so OS cannot directly contact with the hardware, you're saying?
OS
that is possible?
It should not. Generally, it should be through embedded systems. Yeah.
Okay. Got it, sir. Understood.
Now, so as I said, when we want to use this application, processor starts executing the binary file. Now, how does processor know where is the binary file is present? So processor is configured with the location. Processor has some registers where we can configure the location from where to pick the, start from where to start reading the image. See that this is an image file, right? The binary code is nothing but an image file. When we say image, what is that image? Example is some series of 10111. This is an image kind of thing. So that image is loaded somewhere into the memory. In my laptop, somewhere in my RAM or DDR or anywhere or in the flash memory, this application image has been loaded. Whatever software I'm running, that application image has been loaded. This is where it started loading. We loaded from. My processor should know that from here I have to go and perform the reads. Okay, it is the embedded systems which will do that loading, which will tell where the application is present, from where you have to fetch. All those things it does. Once it is done, once this transfer is triggered, it starts fetching those instructions. Next, it will read the next 4 bytes, next 4 bytes, next 4 bytes. It will start reading the complete application and starts executing it. And finally, as part of that execution, it starts getting the inputs, whatever inputs user is providing, and finally does that calculation, and again it returns the output to the user in the reverse manner. I mean, hardware, it goes to the embedded system level, from embedded system it goes to the next level, and finally we have the output getting printed. Now it happens so fast that we don't really notice that something like that is happening actually. So this is a basic idea about applications in the SOC. So restraint billing software. In summary, application or software developed using C, C++, or Java. There is a compiler used to compile this C program to assembly code specific to the processor ISA. Assembler is used to convert assembly code to binary image. Linker maps all the binary files, output the final binary image. Each binary has function calls to other binary. Linking is mapping. Linking means mapping all these binary files is what we call as linking. This binary image is loaded into the SOC memory. If you see SOC stands for what here? System on chip. System on chip has various types of memories. The operating system takes care of memory allocation. Memory allocation means if I'm running MS Office, which memory it should be loaded into. Should it be loaded to, let's say, example types of memories are flash is one type of memory, DDR is one type of memory, cache is one type of memory, hard disk is one type of memory, various types of memories. But when we say the memory allocation, mostly we are talking about this application, these memories only, because hard disk is mostly for storage purpose. Finally, all the access will happen through either flash, DDR, or cache memories only. So it is the operating system takes care of the memory allocation. So if I take MS Office, it is the operating system which tells which part of the DDR that MS Office should be loaded into. Even when I say, if I invoke calculator, it is also one application, right? Which part of the memory, which part of memory, which memory, and what part of the memory, and what part of the memory it should be loaded to. When we say which memory, what part of the memory, we are essentially talking about the binary file of calculator application. See, calculator till one point it's a C program, or when we go down to the binary level, to the image level, it's a binary file of calculator is loaded into that memory at that specific location. Now the processor starts, so processor knows where this application is loaded, and it starts fetching the instructions. That is where when we go forward, we will see that there is processor has some concept called as program counter, which indicates what instruction to fetch. Okay, in between there will be something called as interrupts, exceptions, and traps. All those things we will also talk about all those things as we go forward.
So one basic doubt. So if we talk about SOC, Yeah, just like DDR is a part of a SOC, or it is separately talking to the DDR is talking to the SOC separately.
Actually, DDR is connected to the SOC. DDR controller is part of the SOC. DDR is treated as an external memory which is connected to the SOC.
Got it. So same applies for LPDDR. LPDDR controller will be part of the SOC, which will talk to the DDR, LPDDR.
No.
Main code.
No. LPDDR and DDR you should not confuse. See, DDR itself is two types basically. One is called as PCDDR. One is called as LPDDR. Generally, when we say DDR, we are talking about PCDDR. I mean, what is PCDDR? The DDRs which are targeted for personal computers. LPDDR is the one targeted for low power DDRs. Both of them are two types of DDRs. What I'm telling is, my SOC will have a DDR controller. Now the DDR controller can be PC DDR controller or LP DDR controller. Finally, here you are going to connect the DDR memory. So now I'm calling this whole thing as SOC. It is connected to the SOC. But at a bigger picture, at a bigger level, when you see this whole thing is a system. For the person who is looking at embedded as an overall system, for him DDR is also part of the system.
Okay.
If I look from a hardware perspective, if I'm as a hardware engineer, if I look from my perspective, as an SOC, for me DDR is outside my SOC. But from an operating system level, everything is inside the system.
Got it. Understood.
So binary image is essentially a series of processor specific instructions. So when we say binary image, these are the instructions. What are the instructions we are talking about? Something like sub, something like load, something like store. There will be many such commands which we will talk about as we go forward. So the learning RISC-V is all about see, there will be maximum, there will be at max 200 instructions maximum. Okay, example is what? Load is one instruction, sub is one instruction, add is one instruction, store data is one instruction. There will be such various instructions will be there. Understanding, I mean, instead of just reading everything, how to categorize, understanding how to categorize these instructions is first thing. So as we go forward, we will see that there will be something as L type instruction, R type instructions, M type instructions. Okay. So there are various types of 6 or 7 types of instructions are there. So how to categorize them into various types of instructions? That is the first thing we will need to understand. Not, I think S types are S type is okay. Then again, all the instructions are two types. Are majorly two types. Now you may say you are telling already 6 type, and again you are telling all the instructions are majorly two types. There are two different classifications. See, if you have a one person, he can be the people can be classified in two ways, male and female. Now the same people can be classified, this set of people can be classified as youngsters, someone who is between 10 to 20, let's say, someone between 20 to 30, someone between 30 to 40. So the same set of people can be classified in different ways. That's what I'm doing. Same instructions can be classified based on L type, R type, S type, and some more types. Okay, the same instruction can be again classified into two types. The one which only works with register access, the one which involves registers and memory access. So like that, I mean, it's all about learning. RISC is all about getting the top level picture and understanding the significance of each of those and ability to map those concepts to individual instructions. And finally, that should give you a good understanding of what each instruction does. And then you should be able to develop, we should be able to develop programs directly using RISC-V assembly language, RISC-V instruction set. That is the our final goal of this training, where we understand the various instructions and we are able to develop some of the requirements directly by means of RISC-V instructions. Instead of doing it using C language, then compiling, instead of this, we want to directly develop RISC-V instruction set, because when you go to the projects which are based on RISC-V, you need to have a good understanding of what does each instruction does, what is the significance, all those things. That exposure you will be able to get by developing some programs directly in that language. So when you are able to develop that, you know the language, I mean, you are kind of comfortable, that's why you're able to do. So the debugging will also become easy for us. Next. Okay, let's move on. Okay, now let us understand the significance of processors in SOC. What happens is, processor, after booting up, it starts fetching instructions from the memory. Processor uses program counter to fetch the instructions from the memory. Processor has something called as program counter. Any architecture you take, any ISA you take, there will always be something called as program counter, which will be used to fetch the instruction, and that will tell to the processor what to do now. The program counter, let's say there is a memory here, my processor is there, here instructions are there, my application is loaded. So the program counter will tell me, from this location now read the instruction. The next program counter will be +4, next program count will be +4. Now why am I telling +4 is because each time you are going to get 32 bits of information. 32 bits means 4 bytes. Generally all the processors works on a byte address mapping. When we say byte address mapping, 4 bytes will require 4 address locations. So if the current address location is 100, the next address location will be 104. That is where the instruction will be present. If the current is 104, the next instruction will be present at 108. So it is the program counter which keeps incrementing 100, 104, 108, and keeps fetching those instructions from the memory. And it is the role of the processor to understand that instruction, what instruction is coming. Is it a addition instruction? Is it a subtraction instruction? Is it a load instruction? And do the required activity. That is how finally our application is getting executed. So where is the application is loaded? Can you tell me? Is the application loaded into the processor, or is it loaded into the memory? Can you tell me?
Loaded into the processor.
In the memory.
Loaded into the memory. Whose responsibility is to allocate this memory ranges? I mean, where this application will be present, whose responsibility is it? Is it the responsibility of the application, or is it the responsibility of operating system, or is it the responsibility of hardware?
Operating system.
Operating system, as I told you, it is the responsibility of the operating system to tell that this place is for calculator, this place is for Microsoft Office. Now my embedded system would configure processor with this information. It will tell that, see, calculator is present here. Now you run the calculator application, because at the top level someone is using calculator. See, now I am not using any calculator. So my processor is not doing anything related to calculator. Even though in my memory that calculator application is loaded right now, it is loaded, but it is not doing anything, because the program counter is pointing to something else. What is that something else? Let me tell you. That something else is whatever I'm drawing now. I'm using a tool, right, to draw this. That application it is running actually. Now that application is nothing but GoToMeeting application. The one I'm using to do this training, that application is also loaded into my memory, my operating system memory, in the SOC memory, and my processor is executing those instructions. See, when I'm drawing, the time when you see I'm drawing, that is essentially getting done by the processor. It's happened so fast that we don't really notice that it's happening actually. Now,
so the processor will get the interrupt that I have to fetch from the calculator region. So how the processor will come?
It is not the interrupt, because interrupt is when we call it as interrupt when the request comes from the peripheral component level. See, if I have a DDR controller and DDR controller wants to interrupt the processor, that is called as interrupt. When it comes from the embedded system level or operating system level, that will be called as system calls.
System call.
That will be called as system call. Through the system call, I think operating system will interrupt the processor and ask it to do the next application, what needs to be done. Okay, so as I said, processor uses program counter to fetch the instructions from the memory. Once the instruction is fetched, instruction will be decoded and executed. Now, what is an instruction? Tell me. For me, instruction is something like this. When I wrote one example. For me, as an user, instruction for me is, let's say, subtract x5, x5, x10. So what am I doing? Subtracts content of x5 minus x10 and assign the contents of this subtraction to x5. Something like this I'm doing. For me, as a user, I can understand. Do you think my processor will be able to understand what is meant by S, what is mean by U, B, X5, all those things? Does it understand this kind of language?
No, sir.
It doesn't understand. It only understands something called as opcode. It only understands something called as opcode. Opcode is a 32-bit vector. Through the 32-bit vector, they can tell everything. They can tell that this is a subtraction command. It is a first destination is x5. One of the source register is x5. Second source register is x10. So through the 32 bits, we can provide all that information. It's basically something like this. If you add up everything, it may come to totally 32 bits. The out of 32 bits, some part of the bits will tell that it's a subtraction command. Some 5 bits will tell what is the destination. Some 5 bits will tell what is the source. Some 5 bits will tell what is the another source register. I'm just giving some example like this. Okay, the actual command and actual usage may differ, but I'm trying to give you significance of the opcode. So this conversion from the assembly code to opcode, who does? Tell me, who does the assembly code to
Assembler.
Opcode conversion? It is called as assembler. So assembler is by default part of my operating system. It is in my laptop operating system. In my laptop, that assembler is present, specific to the hardware which I'm using in my laptop. Let's say in my laptop I'm using i7 processor. So there will be assembler specific to that processor only. Okay. So the application performance is directly linked to the speed at which processor executes the instructions. If you see, please read this statement. The application performance is directly linked to the speed at which processor executes the instructions. Now, how can we improve the speed? How can we make improve the speed? One is implement processor architecture which executes multiple instructions at a time. What is that can we do? We can implement the processor architecture in such a way that it executes multiple instructions at a time. That will be called as multi-stage pipelining architecture. Typically, companies go for multi-stage pipelining architecture so that they're able to process, they're able to execute multiple instructions concurrently. Second is what? Reduce the size of instruction. When you reduce the size of instruction, what it can do? Since the size of instruction is less, my processor will take less time to fetch each instruction. As the size is less, it will need less time to fetch the instruction, and it will also need less time to decode the instruction. Third thing is what? Process more data per instruction. See, each time you are processing an instruction, whatever data you get for each instruction, data you get as part of the instruction execution, get more data, get 64-bit data, get 128-bit data. So you will be able to process more data per instruction. So that way you can impact the processor performance. Next, processor ISA, instruction set architecture, is all about this concept. Basically, ISA details all the aspects of this implementation. What will be the data size, what will be the instruction, what all instructions are possible, and what each instruction does, everything it talks about. Now in this further continuation to this, so basically processor is a very important part of hardware because the processor performance defines the performance of the overall system. So in that context, let us talk about two types of processor architectures. One is called as RISC architecture, one is called as CISC architecture. RISC architecture stands for reduced instruction set computer. So the term reduced instruction is important here. What does reduced instruction refers to is it uses a small, highly optimized set of instructions. Understand? It uses the small instructions. That is why we are calling it as reduced. Because it is small, we are using the term reduced. And they are highly optimized for specific requirements. We use that kind of instructions, that is called as reduced instruction set computer. Reduced instruction doesn't mean that less number of instructions. It means that the instructions are smaller in size. Instructions are smaller in size and they are more optimized for the specific requirements. So because of that, since we are using small, what is the benefit of that? It always results in a lower memory density. I mean, and it gives the more efficiency with execution of each instruction because they are optimized. Now, what is CISC? Complex instruction set computer. They use large and complex instructions. That's why we are calling it as complex instruction set. Uses large and complex instruction set. See, the instructions in case of RISC is what? Small and highly optimized. In case of CISC, they are large and complex instructions sets so as to execute various tasks using the least possible codes. Okay, so the way I look at it, I mean, I'm not sure how relevant it would be. Let's say we have, for example, English language. It has got 26 alphabet. Using that small number of alphabets and highly optimized set of alphabet, we are able to create any type of English information, right? Any kind of information we are able to define. If you take Chinese language, that I will feel like it's more of a large and complex instruction set. It would be more like, it seems Chinese has more than 3000 characters. Each character indicates one complex instruction. So in case of Chinese, what they do, if they want to do one complete operation, they can represent that complete operation through one symbol that will tell what you want to do. When you go to the same thing in RISC, in case of English, we can put together those 26 characters only and finally get the same behavior. So here the Chinese gets more complex because we are talking about 3000 characters. Here English gets better because you are only talking about 26 characters. So I mean, this is how I would look at it. Okay. So uses large and complex instruction sets so as to execute various tasks using the least possible codes. Finally, you are using the least possible code only. You are using only one symbol to execute the one operation in Chinese. In this case, you are using more number of symbols you have to use. Like I want to go. Let's say you want to write I want to go. You say 2 2 4 1. Totally, how many you are using? 5 space 1 space 1 1 1. So you're using 2 6 7 9 and 2 11. Here you're using only one character. I mean, maybe Chinese has one character which will tell I want to go, but the problem is it is dealing with the 3000 types of characters. So that is where more and more companies are moving towards reduced instruction set computer type of architectures. So lot of architectures that you see these days are based on actually RISC architecture only. There are only two standard architecture which are based on CISC as of now, which majorly the company is using, that is x86. Can you tell me what is x86? Is it RISC or CISC?
RISC.
It is a CISC, right? AMD 64 is also CISC architecture. If you take ARM, it is a RISC architecture. PowerPC. Okay. Even Spark processors, Spark ISA, even RISC-V. These are all RISC-based architectures. Now, let us talk about RISC architecture. The RISC is a reduced instruction set computer, is a type of microprocessor architecture that uses a small, highly optimized set of instructions. RISC architecture allows increase the register set. You can increase the number of registers inside the processor. It increases the internal parallelism by increasing the number of parallel threads executed by the CPU. The RISC architecture allows for us to do these things. It allows for us to increase the speed of CPU execution instructions because it is only processing a small and optimized set of instructions. It automatically helps improve the speed at which CPU execute the instructions. Effectively, we get better throughput out of this. Then what are the RISC architecture example? ARM is an example, MIPS is an example, RISC-V, PowerPC, Alpha. So there are various types of architecture which are all examples of the RISC architecture. Next, CISC architecture. CISC stands for complex computer set architecture. Complex instruction set computer. CISC processor is a classification of microprocessor based off CPU design that operates on large and complex instruction set so as to execute various tasks using the least possible code. Okay. It is based on more than one instruction per cycle execution approach. In one cycle, it can execute more than one instruction. The design of CISC processor is based on the approach to complete whole operation in few lines of assembly language code. Idea is to use minimal lines to complete the operation. To do that, to achieve that minimal lines, to achieve fewer lines, they have large and complex instructions. What is the problem is due to this large and complex instructions, they are typically different sizes. See, like if I tell A, B, C, D, if I write A, B, C, D, all of them take the same space, right? If I write D, all of them are taking the same space in this vertical lines. Whereas if I take probably different characters of this large and complex instruction set, something may be of 64 bit, something may be of 16 bit, something may be of 32 bit. So that may result in a inefficient utilization of the instruction memories. So that is where CISC gets little inefficient. So there are many instructions. CISC has many instructions. A typical representative in Intel x86 architecture. x86 64 is the 64-bit extension of the x86 architecture. It is designed by AMD and it is also known as AMD 64. So this is a brief about what is RISC and what is CISC architecture. Now let us.
Sir, when we say sorry to interrupt. So when we say the ARM RISC processors and RISC-V processor, so what is the difference? Is it in the instruction sets?
Instruction set is different. The way they have implemented the registers is different. The way they have implemented the internal hardware is different. The number of pipelining stages is different. The way they have implemented their arithmetic logic unit is different. All of that will be different because their hardware will be directly related to how the what kind of instructions they have provided. So based on that, it differs. So hence, the fundamental concept remains that both of them are based on RISC architecture only, but their internal implementation, of course, differs. So that means.
So when the operating system.
Yeah, please go ahead.
So when the operating system is converting the particular processor into assembly code, so OS knows that which particular processor is it, and accordingly it is converting it into assembly code.
Yes, exactly.
Okay. Got it.
So now talking about RISC versus CISC, the primary difference between RISC and CISC architecture is that RISC-based machines execute one instruction per clock cycle, and as I told you, the CISC process may execute more than one instruction in a clock cycle. In a CISC processor, each instruction performs so many actions that it takes several clock cycles to complete. So there is no guarantee that how many cycles each instruction may take in case of RISC processor. But in RISC, compulsorily each instruction is executed in 1 clock cycle. In a RISC processor, every instruction also has a fixed memory size. If you take any instruction, I'm talking about basically, the fixed memory size means an opcode of 32-bit size. In RISC processor, each instruction is 32 bits in size, which makes it easy. Since it is fixed in size, it is easy to decode and execute. In CISC machine, instructions can have variable lengths, which increases the processing time. So that is where the RISC is more efficient compared to CISC. So I can say in summary, RISC is an improvised version of the CISC. So what the people who have developed RISC in 1980s, so they have developed RISC architecture in 1980s. So they have developed it to address these drawbacks. So what were the drawbacks in CISC processor? Each instruction you don't know for sure how many clock cycles it takes, and we don't even know what is the size of each instruction. So to address that problem, what they have done is they have broken down those complex instructions into small efficient instructions. So which is ensuring that there is a fixed size for each instruction, and they know that each instruction will take one clock cycle. So that way it also becomes easy for the application developer to know how the code is going to execute, because he knows that each instruction he's going to develop will take 1 clock cycle, and he knows that the footprint of each line he's developing, the footprint, I mean assembly code line, is going to take 32 bits. So it makes it easy for the application developer. Even from a processor perspective, implementation becomes easier. So that is the reason most of the companies are moving towards RISC-based architecture. Next, RISC advantages. I think I'm here trying to sell the RISC, okay, because maybe I'm telling this RISC advantages many times, but it is important for us to know. Okay, RISC provides, first important advantage is RISC provides high performance per watt for battery operated devices when energy efficiency is key. Because as I told, it is efficient in terms of the number of instructions taken per number of clock cycles taken per instruction. It is efficient in terms of the instruction size, and since the instruction size is fixed, the utilization efficiency increases. So overall it results in the high performance per watt. That means if you tell me, I'll give you one simple example. I have 100 watts of power. Using RISC, I will be able to execute 100 instructions. The CISC may not give me similar kind of performance. That's what we are telling, high performance per watt. A RISC processor executes one action per instruction. By taking just 1 clock cycle to complete, operation execution time is optimized. So that can be optimized because you know that each one takes 1 clock cycle. Because the architecture uses a fixed length of instruction, it is easy to pipeline, because you know that each instruction take 1 clock cycle, and you know that each one is a fixed length in instruction. You can pipeline them. Can someone tell me what is meant by pipelining? What is meant by pipelining?
Pipeline is like if one instruction is fetched, then other will be in the decoding stage, and this kind of parallelism we can do. Fetch, decode, and execute at the same time.
Yeah, basically it's a concept. In simple terms, it's a concept where you can divide the whole logic into multiple stages, so that where this is working on one input, the next stage is working on a earlier input, this is working on a different input, earlier input, this is working on a earlier input, which allows for us to process more instructions in a limited time. In less number of clock cycle, you can process more instructions. Now you may say, what if I don't do this kind of pipelining? Then at any time I can only process one instruction at any point of time. So hence the system becomes inefficient. So going forward, we'll talk about what is pipelining. Because the architecture, and because it lacks complex instruction decoding logic. See, there is no complex instructions. because there are no complex instruction decoding logic. It supports more registers and spends less time in loading and storing the values to the memory. The whole idea is we are reducing this complexity, which makes it easy to do other operations. Now for chip designers, RISC processors simplify the design and deployment process and provides lower per chip cost due to smaller components required. Next, because of the reduced instruction set and simple decoding logic, less chip space is used and fewer transistors are required. So that is where you would see most of the portable devices. When I say portable device, can you tell me any portable electronic device?
Laptop.
Actually, mobile phone is something you keep it in your pocket and carry it, right? That's an example of portable electronic device. Okay, so all those kind of devices which are very power what do you say, power intensive. What is mean? I mean power consumption intensive. That means power saving is very important. All those things definitely uses RISC based processors. Even these days you will find laptops are also coming with RISC based processors only. Now so far we discussed about RISC versus CISC. Now let us talk about why are we moving to RISC-V when we already have ARM processor, when we already have PowerPC, when we already have other architectures. Why do we want to go for a new architecture called as new ISA, called as RISC-V ISA? If you see, most of the RISC-based SoCs are currently based on ARM architecture. If you buy any RISC-based electronic system, there is a chance that 95% there is a 95% chance that that electronic device is using ARM processor. Even it could be more than 95%. Okay, when you use the ARM architecture, when you use ARM ISA or when you use ARM architecture, the chip manufacturer, the company which is manufacturing the chip, needs to pay a royalty of 1 to 2% to the product cost. 1 to 2% of the product cost. So for every electronic device you are using and it has got an ARM processor, that royalty amount, 1 to 2% of that product cost, goes to the ARM company. Okay, like you see, Windows has monopoly and operating systems. So to counter that monopoly, a Linux open source operating system was implemented to address this monopoly. Similarly, ARM has monopoly in the RISC-based architecture. Okay, many companies, in many cases, companies wants to reduce the dependency. They want to do something and make sure that ARM should not have that monopoly. To reduce dependency on the ARM-based architecture, hence some of them are companies are adopting RISC-based architecture. One is what? They don't want to have some company to have monopoly in something because they become dependent on ARM, right, for everything. That's the first thing. Second thing is the royalty they have to pay. That effectively cuts down their profit margins. Whereas RISC-V is a free open standard ISA. That means it doesn't require to pay any licensing fee or any royalty to anyone. Anyone can freely use their ISA, their instruction set, and based on that they can implement their own processor architectures. RISC-V ISA is implemented to address this monopoly. Okay, even though it's not as easy as it's said. I mean, you may say when someone is paying 2% or 1% to the ARM, they provide their own value. I'm not telling that it comes for free. In RISC-V, the cost is you have to implement the processor using that ISA. So that cost will be there. But then eventually in the long term, when you develop your own processor architecture to support that ISA, your investment is done. You don't have to pay ARM like you're paying to ARM. Anything you do when you use ARM processor inside your chip, the payment should be done to ARM as a royalty fee. Here, once you have developed this architecture, once you have developed the processor, you don't have to pay anything to anyone. So that is the reason why companies want to move to RISC-based architecture. And you see there is a lot of traction where many companies have started working on RISC-V based SoCs. Even in the big product companies, which traditionally used to be only ARM based SoCs, they have started working on RISC-V based processor SoCs. Now let us start with the term ISA. Let's understand what does ISA stands for. The ISA stands for Instruction Set Architecture. The one thing about ISA is ISA doesn't tell us how the hardware is internally implemented. Now, what does ISA doesn't tell? I told you right initially, I told that ISA talks about these things. Various types of instructions, the length of instructions, what are the types of instructions, what are the extension. But ISA won't tell you how Verilog coding should be done, what all subcomponents will be there, how the pipelining will be done. The internal aspects of implementation, it won't tell you. It will give you a bigger level picture of how RISC processor is going to work. So that you need to understand. Now, what does ISA define? What do you get as part of ISA? The ISA acts as an interface between hardware and the software. Basically, it tells how CPU is going to control the software. How CPU is controlled by the software. ISA provides the way for user to interface with the hardware. User should know the instruction set architecture through which he knows how I can develop applications so that I can work with the RISC architecture. That is what is defined as part of the ISA. What do I mean by that interfacing? I should know how many registers are there, how many instructions are there, what is the significance of instruction, if I want to load a memory, what type of instruction should I use? If I want to perform an addition, what type of instruction to use? If I want to do floating point multiplication, let's say if I take the same computer, same laptop, and I do 3.5 into 5.5, it is doing inside my laptop a floating point operation is happening actually. So there are some floating point instructions corresponding to my processor inside my laptop that is doing this operation. So ISA talks about all those things. So the person who has developed this calculator application, he would have thought about all those aspects. If I want to do 3.5 into 5.5, okay, which register should I use to load 3.5? Which register should I use to load 5.5? So for him it's not the 3.5, and for him it's not 5.5. For him it's a number called as A, for him it's a number called as B, two numbers. So A, where to load A, where to load B, how to do A into B multiplication using this architecture, ISA architecture, and finally how to get the output and how to display the output to the screen. All those things you would have thought about. Okay. Now ISA defines supported data types. When I say supported data types, integer, floating, double floating, all those things. Sorry, single precision floating, double precision floating, all those things it talks about. And the registers, how the hardware manages the main memory, which instructions a microprocessor can execute, and input and output model, how it is going to take the user inputs, and how it is going to give the outputs. All those things ISA defines. Why ISA is important? See, understanding what the instruction set can do, and how the compiler makes use of those instructions can help developers write more efficient code. See, if I understand the instruction set architecture, what all things I have, I will be able to utilize those resources properly. So that is where understanding of ISA is very important. Next, what are the existing ISAs? x86 is existing, ARM, Spark, MIPS, OpenRISC. So the new one we are talking about is the RISC-V architecture. We don't call it as RISC-V, we call it as RISC-V. Now let us talk about RISC-V ISA, the ISA specific to the RISC-V. So RISC-V ISA has to compulsorily support base integer ISA. When I say base integer ISA, I mean to say every RISC-V ISA, that means any RISC-V based processor must support base integer operations. Base integer operations means what? It can be RV32I, meant for 32-bit with 32-bit integers. RV64I means 64-bit integers. So when I say RV64I based RISC processor means 64-bit addition to 64-bit addition. These kind of operations, addition, subtraction, multiplication, division, all those things must be supported. That is the compulsory requirement of the RISC-V ISA. Okay. Can you please read this once? Read this whole thing once, I'll explain. Okay. So RISC-V ISA, the primary thing it should support is base integer ISA. That is called as RV64I. RV stands for RISC-V. 64 means 64-bit integers, I means integer. And other than that, it supports various extensions. The extensions can be like multiply extension instructions. I mean something which supports the multiplication operations, and something which supports single and double precision floating point extension. RV64F, RV64D. And other than that, something called as pseudo instructions will be there, like some move commands which doesn't fall into any of those categories. They are called as pseudo instructions. Because if you are moving something, you're not doing anything, you're just moving something, right? So those things fall under pseudo instruction category. Now every instruction consists of an application binary interface. This keyword is important, application binary interface. What does application binary interface tells is the person who is developing the application, how does he interface with the binary level of the code? What is the connection between the application and the assembly level code, the RISC-V level code? That interfacing is called as application binary interface. For that purpose, there are some special registers are there. Registers and special registers are there. They are called as A0, A1. It's not AT, it's actually A1, SP, RA. SP stands for stack pointer. Okay. RA, S0, FA, FA5, FA4, FA5. So there are various types of registers are there. RISC-V has X0 to X31 registers. In fact, these registers are nothing but this X0 to X31. Now you may say there are 32 here, there are 7 here. How can they map? I have written only 7 just for our convenience. Ideally, if you write everything, it will come to 32 registers. So these 32 registers is how an application developer can interface with the processor directly. If as an application developer, if I want to run something, I can do that by directly accessing those registers. So instead of calling them as X0, X1, X2 like that, we refer to them in terms of A0, A1, SP, RA, S0, FA4, FA5. Each of them is mapped to one thing. Maybe A0 is mapped to X0. SP is mapped to X1. So like that, each register is mapped to 11 X, X0, X1 like that. Next, RISC-V has X0 to X31 registers. The names given to these registers using which application can be developed while directly interfacing with the hardware. That means it allows for me to develop an application and where I can skip the operating system and I can directly interface with the hardware. That kind of thing is called as application binary interface. So the application binary interface, see, some part of the ISA is available to the application developer called as user ISA. Some part available for OS developer called as user and system ISA. The application program has access to the hardware resources through system calls. See, whatever applications I'm running, when I want to access the hardware resources, there is something called a system call through which An application can access the hardware resources. It is also called as application binary interface. This application binary interface and system calls are essentially referring to the same thing. ABI accesses the registers X0 to X31. Instead of calling them as X0, X1, X2, X3, they will use a special terminology called as A0, AT, SP. SP means stack pointer, RA, all the various types of registers are there. Next, RISC-V instructions. Okay, so RISC-V instructions. Let us understand some basic concepts about instructions. So finally, all these instructions are about doing some operations like addition, subtraction, multiplication, to the power, division. Finally, everything may come down to these kind of operations only, and then doing some decision making, branching, all those things, right? All these instructions, whatever we are talking about, they can be divided into two categories. And first, primarily, you need to understand that RISC-V uses load store architecture. You will come across this terminology. This is one of the type of architecture which is called as load store architecture, which divides the instructions into two categories. That is, one type of instructions is called as memory access instructions. One type of instructions are called as ALU operations. When we say memory access instructions, load and store between memory and registers. So when we say load and store, load means this is the memory. My RISC processor has 32 registers. If you take any RISC processor, it has got 32 registers. Every RISC-V processor has 32 registers. These registers are named as X0, X1 till X32. Sorry, X till X31. Okay. These registers, other than that, my system has a memory. My system has memory. Okay. Now, when you have two things basically, registers and memories. Any instruction that we implement can work in two ways. Can work in three modes, right? Three modes totally. One is only using registers. Don't use any memories. That instruction won't use any memories. Only using memories. Using both registers and memories. Now, RISC only supports these two. So, or rather, I would say RISC doesn't support this. RISC-V doesn't support this, where it doesn't do any instruction where only memory is involved. It always involves at least one register during any of the instructions. Those registers are X0, X1 up to X31. Next. So majorly we can divide those into two categories. I told you, right? These are the two categories. So the first category is what? Memory access, where load and store between the memory and registers. Load means when you move the data from memory to registers, it is called as loading. When you move the data from register to memory, it is called as storing. So you are storing the contents of registers into memory. You are loading the contents of memory into the register. So that is how you read it. Those kind of instructions called as load store instructions. The other type of instructions are called as ALU operations. ALU means what? Arithmetic logic unit operations. They involve only the registers. They only involve the registers. Add. Tell me, what do you think add will be? Do you think add is memory access or add is ALU operation? Can you tell me? What is add?
ALU.
It will be ALU. If I do sub, what will be the type of ALU operation, right? So whenever I know that it's a ALU operation, I surely know that it only involves the registers.
When I know that something is a load store instruction, I know that it involves memory and it involves register also. So you need to, when you read the instructions, you need to categorize. Is it a memory access instruction? Is it a ALU operation? So accordingly, you know whether only registers are involved, whether both memories and registers are involved. So what is load store architecture? Load store architecture, it is used for efficient utilization of the limited number of registers. You may say, why do you want to work with memory altogether? Why don't we just do everything with ALU? But the problem is, why don't we just do with only registers? The problem is I have only 32 registers. With 32 registers, you can't do many operations concurrently, right? Whereas by involving memory, my memory is huge in size. So it will give me flexibility to do lot of things concurrently. Next. It is used, load store architecture is used for efficient utilization of the limited number of registers. See, I have only 32 registers. I want to use those 32 registers efficiently. Why number of registers is limited? See, why are we limiting it to 32? You may say, why don't we keep 3000 registers? Instead of 32 registers, let me keep 3000 registers. The problem here is the whole compiler, everything gets very complex, because when application developer is developing an application, now he knows that he has to target only these 32 registers. Had it been 3000 registers, so he had to understand all the 3000 registers and implement as per those registers. So the application development, everything becomes very complex because of that. So the application developer and OS interfaces with ISA through these registers. As we increase the number of registers, application development becomes complex, requiring larger memory footprint, and even the overall development becomes complex.
Srinivas, I have one question here.
Yeah.
So when you say a load and store between memory and register, so it is a like processor specific memory or system memory?
It can be any memory. It can be any memory.
So let's say if it is a system memory, it will take a lot of time to execute those
No, see,
instructions.
when we say system memory, we are not talking about the hard disk. At best it can be DDR. At best it can be DDR. So DDR is also quickly accessible, relatively quickly accessible. So that is the cost you have to pay when you want to see, you are trying to reduce the footprint. So that is a cost you have to pay. Sometimes load and store won't be as efficient as ALU operation, because ALU operations involves only registers which are immediately accessible. Those operations will be quick, and this load and store will be less. So probably in your case, in what you are telling, we may have to reduce the number of load and store instructions per program you do, and we should do more of ALU operations and less of load store operations to make the program efficient.
Okay. So who decides this memory, like whether it has to use the cache or it has to use the DDR? Like who decides this one?
It's application developer develops, right? Basically, it is the application developer tells it is, we develop like at this, from this memory, load the content into this register, store this content from this register to this memory location. So I do it. So when I do it, I know what is this address maps to.
Okay.
Yeah. Next. So we have talked about this. Next. So some summary about RISC-V instructions. RISC-V base instructions. Basically, it supports 64-bit integer data operations. This is bare minimum. I mean, you cannot have any RISC-V processor without support for base integer operations. Okay. There are two ways to load 64-bit number into the registers. Load the 64-bit number directly, store the number into memory, and access it from the memory. Load register from the memory. Basically, one is loading, one is load the 64-bit number directly into the registers. So how number can be loaded from memory to register, all those things. Let us discuss about all these aspects, how the instructions work and how this concept of load and store works, everything in the next session. So I will be stopping the session here. In the next session, we'll continue with further aspects of the RISC-V instructions. So if you have any questions, I can answer those now. Okay. Any questions you have?
So sir, this is a demo session and first session both, right?